Now, as the title implies, this technique reduces a higher order equation to one that we've already studied techniques for solving. Now let's start with some more terminology. We're going to take a look at these linear differential equations and see what do we mean by homogeneous. Well, all of these are what we would term higher order. The first one is second order because it's a second derivative. The third one is a third derivative, second derivative, third derivative, third derivative. Now remember, the exponent, when it's in parentheses like this bottom one, means the fourth derivative, not y raised to the fourth power. That would be a 4 without any parentheses on it. Now, the term homogeneous refers to the fact that we have the stuff that's over here equal to 0. Now that raises some interesting things, because one obvious solution here is y equals 0, because if y was 0, the second derivative would also be 0, and 0 would be equal to 0, so y equals 0, obviously always a solution. That's kind of where it gets its name, homogeneous. However, again, you can kind of tell on each of these it's homogeneous if it's equal to 0. Well, the one here is not equal to 0, so it is not homogeneous. The next one is not equal to 0. It is not homogeneous. Now the next one is a little tricky looking. If you look, here's the third derivative, here's the function itself. Well, the 3x, if you put it in a standard form, would be over on the right hand side, and so we'd have the third derivative plus 2 times y equal to 3x, and so likewise that's not homogeneous. Now this will seem like quite a detriment to the technique that we're about to learn. However, keep in mind, in future chapters we're going to see how to overcome this limitation. Now here's a summary of the technique that we're about to take a look at. Let me show you what the process looks like with this second order homogeneous linear equation. First, we're going to recognize what our interval of validity is. Now, the coefficients of the derivatives and of the y have to be continuous, and x squared, negative 3x, and 4 are continuous for all values of x. Also, the coefficient of the y double prime, the second derivative of y, cannot be 0. Well, since x squared can be 0 when x is 0, our interval of validity, our place where solutions can occur, is all values of x except for 0. So here's our substitution. Given that one solution is y equals x squared, we're going to make the substitution x squared times u, which means we need the derivative and second derivative, and then substitute into our differential equation and simplify. notice we come up with a second order equation much like the ones we have done in an earlier chapter, which we should now be able to solve by previous techniques. Now, to use the substitution method from chapter 11, we can't use u because we've just changed our equation from y's to u's, so we'll use v instead. And so we'll use u prime equals v, u double prime equals v prime, do the substitution, and have a first order equation which happens to be separable. We'll recognize constant solutions, separate it, integrate it, and then finish solving for v, and then start substituting again. So in place of the v, we'll use u prime, we'll integrate that, and finally we'll take this u and combine it with the x squared to get our solution. Now the process is the same for non-homogeneous equations. It just has a little different workings. Okay, so let's again begin by checking the interval. Now this is the same one that we just got through doing on the left hand side anyway. And then use the substitution just like we did before. And you notice this time we simplify and we get a little different looking differential equation. So we'll still use the substitution method. Only this time it's not separable like previously. So we're going to have to find some other way of solving that differential equation. Well, that is a linear differential equation, so we can find the integrating factor and then change this and integrate. And once we find the v, we need to substitute the u prime in place of the v, integrate again, and then go back to our original substitution, x squared times u, and use what we just found for u. There's quite a bit of algebra involved in these two steps, and we can expedite the work by doing a little bit ahead of time. Now for this to work, we need to rewrite our original equation so that the coefficient of the second derivative is a 1, and then we will come out with some function that is a coefficient of our first derivative and some function that is a coefficient of y. We will then take the derivative of the y1u generically, that means just by the product rule, and then the second derivative of that, substitute those into our derivative equation, and then do some simplifying. If we multiply out and collect like terms, we'll have the u double prime on the front, then the u primes, then the u's. Group those together and factor the u prime out of these two, factor the u out of these three, And notice that on the end, the y double prime plus py prime plus qy is exactly like what we started with, which we know is equal to 0. So that takes all of that out of the picture. And we end up with this template, which we can use instead of going through all the algebra that we just went through. And so let's see how that would work on a problem. So what we'll do is we'll still be doing the substitution. Y equals y1 times u, in this case y1 being the x cubed. So u is equal to y over x to the third. Then we'll divide our original equation through, in this case, by x squared, and just recognize what our y1 prime and p are. Here's the little magic formula that we came up with. We're going to substitute into that. The y1 will be the x cubed. The y1 prime will be 3x squared. And the p will be negative 6 over x. So substituting those and doing a little simplifying, here's a 6x squared, here's a minus 6x squared, which comes out to be 0, and then dividing through by x cubed, integrating both sides, and integrating again, and then replacing the u with the y over x cubed, like we said in the beginning, and solving for y.